morning, everyone. My name is Erica O. Capiral, and I am here to present to you the user interface of an Android. Android user interface is based on direct manipulation, which means that objects of interest in the UI are visible and can receive immediate feedback. Android is designed primarily for touchscreen mobile devices such as smartphones, tablet, and computers, with specialized user interfaces for televisions, cars, and wristwatches. The OS uses touch inputs that loosely correspond to real-world actions like swiping, typing, pinching, and reverse pinching to manipulate on-screen objects and a virtual keyboard. Every Android iteration, UI also evolves, the latest being the new Android 12 iteration that has the most advanced UI upgrade. Google claimed it their most personal OS ever. Android newest version features dynamic color capabilities that can transform experience based on wallpaper and responsive motion that responds to touch. And with a more spacious redesign, color contrast optimization, and new features to help those with low vision, Android 12 is designed to be accessible for even more users. Before letting you see the latest Android, which is the Android version 12, let us first go down through the evolution of Androids. First, we have the Android version 1.0 and 1.1, which was released in 2008 and includes the Google apps like Gmail, Maps, Calendar, and YouTube. Android version 1.5, named Cupcake, is released in 2009, introduced the first on-screen keyboard and the first ever option for video recording. Android 1.6, named Donut, was released in the fall of 2009 and introduced Android's first universal search box. Android 2.0 to 2.1, named Eclair, was released in October 23, 2009 and introduced the first versions of turn-by-turn navigation and speech-to-text. Android version 2.2, named Froyo, was released 4 months after Eclair and introduced the first voice control wherein people can only tap an icon and then command the gadget to do an action. Android version 2.3, named Gingerbread, was released in 2010 and used the color of Android, which is green, and became visible to the Android's 2.3's user interface. Android version 3.0 to 3.2, named Honeycomb, was released in February 2011, became a tablet-only Android, and changed the green user interface in Gingerbread into a holographic design. Android version 4.0, named Ice Cream Sandwich, was released in October 2011. Android united tablet and phones to have a single user interface vision and introduced app switching. Android version 4.1 to 4.3, named Jelly Bean, was released in 2012, introduced quick settings and the lock screen widget feature. Android version 4.4, named KitKat, was released in 2013 and now has a lightened home screen and the new Google Now panel. Android version 5.0 to 5.1, named Lollipop, was released in the fall of 2014 and introduced the new material design standard of Android. Android version 6.0, named Marshmallow, was released in 2015 and introduced the Now on Top, which allows the user to screen search. Android version 7.0 to 7.1, named Nougat, was released in 2016 and introduced the split screen mode and data server feature. Android version 8.0 and 8.1, named Oreo, was released in 2017 and introduced the picture-in-picture mode and a notification snoozing option. Android version 9, named Pie, was released in August 2018 and now has a hybrid gesture or button navigation system. Android version 10 was released in September 2019 and introduced the new privacy permission model. Android version 11 was released in September 2020, focuses more on privacy including access to the user's location, camera, and microphone. And for the latest Android version that we have now is the Android version 12, released in October 2021 and now offers a new look and feel for the operating system. Android 12's complete features includes personal material view, dynamic color, responsive motion, conversation widgets, accessibility improvements, safe, mic and camera indicators and toggles, approximate location permissions, privacy dashboard, private compute core, enhanced gaming, scrolling, and lastly, screenshots. That is it for the user interface of an Android.
Hi, I'm Ronnie Kiming, and today I'm going to present process management on Android's OS. So, Android's process management sits somewhere in between Windows and Apple iOS mechanism in managing processes. This means that apps running in foregrounds are prioritized, but apps have much more freedom to run in the background than they do on iOS, wherein it only allows apps to perform a few limited tasks in the background, thus making Android more flexible and have the availability to preserve certain data or processes that sit in the app for a much longer time. Second thing I'm going to impart on Android's process management is its partition to system resources. Android integrates automatically in managing processes, which means that system resources allocation is greatly implemented widely. Android does a good job in killing or terminating processes that are least prioritized, thus resulting in having free memory allocation that is needed especially in opening or running heavy duty apps like COD, for example. So one great example onto how Android implement this is when playing a heavy and resource hungry game like Call of Duty on a device without much RAM. The OS itself will start terminating service processes like streaming music or file download in order to accommodate and give the necessary resource on the game. This mechanism of Android's OS in process management proves how good they are in managing resources without the intervention physically by the user. So that's how Android manages processes, and next presentation will dig deeper on importance hierarchy and other mechanisms regarding process management on the OS itself. Thank you and have a good day.
As we dig deeper about the Android process management, we will talk about how Android apps can be processed at the same time while other OS cannot. One example of this is when the user plays a game, let's say Call of Duty. While they are playing but wanted to use Facebook, the running application would be Facebook and the game would stop playing. In most cases, every Android app runs in its own Linux process. This process is created for the application when some of its code needs to run and will remain running until it is no longer needed and the system needs to reclaim its memory for use by other applications. To determine which process should be killed when low on memory, Android places each process into an importance hierarchy based on the components running in them and the state of those components. So now let's talk about the processes. First is the foreground process. Foreground process is required for what the user is currently doing, and it can be called a foreground process if it is running an activity. Next process is the visible process. It is responsible in doing work that the user is currently aware of, so killing it would have a noticeable negative impact on the user experience. There's still more to find out about the other processes that will be presented by the next presenter. This is Anjali, thank you.
Another process is the service process. These are not directly visible to the user, are generally doing things that the user cares about, such as background network data upload or download. So the system will always keep such processes running unless there is not enough memory to retain all foreground and visible processes. Sometimes our phone is experiencing sudden stop and displaying a button, force stop. Maybe because too many applications are open and the memory data can handle it anymore. So sometimes service process stop. However, the cache process is the one that is not currently needed, so the system is free to kill it as desired when resources like memory are required elsewhere. Cache is a temporary memory wherein, even we erase it, nothing will lose that will make a good function to our application. Let's watch the video example that we created before we talk about the third process management.
Everything is out and sour. I just really express. Oh, don't look at the bummer. I gotta start and burn. You wanna start with love. Maybe that's over. Oh, look, give us a fire. Even if we break, we always knew. But we under pressure, we sure true. We all diamond, no hide, no truth. No, here's a pill, we go away, we need to play it. Yeah, we come and go. Why you keep bringing what for? And if you think it's not enough, fill it up now. And if you think you can do a thing you wanted to do, just break it down.
We saw that even we open other application, the foreground process. Now, let's talk about the third process management. Android apps can start in response to events. Android apps can also start in response to events. For example, a developer can program their app to automatically run at the startup and run a service in the background. Apps can start in response to other events such as when you take a picture, when your data connection changes, and so on. These allow apps to perform actions in response to events without running in the background constantly.
Android allows every user to access their device's file system using a file manager. They can access Android files and transfer them between a computer and a smartphone or tablet. This is performed by simply plug in a USB cable and an Android device and fire up your desktop file manager. Android File Manager app reacts as an important part of the software on the device. It provides facility to browse files, manage storage, space downloads, move files around, and a lot of other activities. Supplementing Android's local storage, one little-known feature of Android is its ability to connect with external storage devices like USB memory sticks and even larger capacity portable hard devices. Android provides its user a wide variety of options to expand their memory allocation by adding or inserting memory card or putting files on your removable flash drive with the help of various files manager application available for free that can access, move, rename, and encrypt files depending on your like. Android uses a file system that is similar to desk-based file system on other platforms. Option to save app data. App. Specific storage. Store files that are meant for your app's use only, either in dedicated directories within internal storage volume or different dedicated directories within external storage. Use the directories within internal storage to save sensitive information that other apps shouldn't access. Shared storage. Store files that your app intends to share with other apps, including media, documents, and other files. Preferences. Store private primitive data in key-value pairs. Databases. Store structured data in a private database using the Room Persistent Library.
Directory structure. Android uses the Linux file and directory structure, which consists of a single root. All drives and partitions are displayed as directories in this tree-like structure. The system partitions and directories are protected, and unless your device is rooted, you don't normally have access to the seal, though some file managers will display them. Physical disks and partitions appear under the root as directories, and do not have a drive ladder as in Windows. Since Android is a Linux-based operating system, your handset features a Linux SD file system structure. Under this system, there are 6 main partitions on every devices, which is boot, system, recovery, data, cache, and MISC. The first partition is boot. This partition contains the kernel, RAM disk required for the phone to boot when powered on. The second partition is system. The system partition houses the operating system files, also known as the ROM, which includes the Android UI and other pre-installed applications. The third partition is recovery, an alternative option to booting into the OS. The recovery software can allow the user to backup and restore other partitions. Fourth partition is data. The data partition saves user data ranging from contacts and messages to apps and music. It is the partition you can access via a file browser. This sector is wiped when performing a factory reset. The fifth partition is cache. Android stores frequently used data and app components here. This can be wiped to fix certain issues and is automatically rebuilt and updated over time. The last one is MISC. This partition contains other important system setting information such as USB configuration, carrier ID, and other hardware settings, usually saved in the form of on-on switches.